saying quantization of Poisson Hopf algebras and moduli spaces of flat connections. And please don't forget to mute your mics, as I will be doing now.
Okay, thank you very much. So yes, I'll tell you about this quantization of Poisson Hopf algebras and how it relates with moduli spaces of flat connections and a bit with Chern-Simon's theory. Now let me just start with this first part about quantization of Poisson Hopf algebras, which we did with my student Jan Pullman. So what is a Poisson Hopf algebra? Oh, well, you should just imagine the algebra of functions on a Poissonly group, but formally speaking, it's a commutative Hopf algebra, which has also a Poisson bracket and which is compatible with the coproduct. So the coproduct is a morphism of Poisson algebras. And this quantization problem, which we're trying to solve, is to deform the product, and we also need to deform the coproduct and the antipode in such a way that we get, again, a Hopf algebra, but this time non-commutative, and it should be deformed in the direction of the Poisson bracket. So the first order part of the commutator should be the Poisson bracket. And there are some further requirements, but which actually make things simpler rather than more difficult. All these MNs, delta Ns, and SNs, all those terms, they should be given by some nice universal expressions. So they should be simply compositions of the maps which we had in our original Poisson Hopf algebra.
So it's probably too early, but I already have a question. May I?
Yeah, great. Okay.
Right. No, but so right, M naught is a product of our commutative Hopf algebra. Delta naught is its coproduct.
Yeah.
Right.
Mm-hmm.
So the Poisson bracket tells us something about M1.
Yes.
But then there is also a priori delta 1, right?
Yeah.
But nobody tells us anything about delta 1. Is it right?
Yes, that's right. And actually, it will turn out that's probably true for any natural quantization that delta 1 is equal to 0. But delta 2 is non-zero.
Mm-hmm. Okay.
But yes, that's just, yeah, somehow. Okay, let's leave it like that. So we want to find somehow some nice expressions for each of those MNs, delta Ns, and SNs in terms of the original things that we had, also using the Poisson bracket. And maybe like linear combinations of those with rational coefficients. Now, to what extent is this a solved problem? So there is a famous thing done by Ettingov and Kazhdan long ago when they quantized Lie algebras, which doesn't quite solve this problem. It somehow solves it for some sort of functions on a formal group. So, but in the end, one can say that our solution should be judged to be interesting or not based on the method. So whether that method is interesting or not. So let me tell you how we did it. We were using somehow simplicial methods. So let me start with just recalling you or telling you how one assigns to a group a simplicial set and how one can reconstruct the group back from the simplicial set. So the simplicial set is called the nerve of the group. It's denoted by this N. So it's a contravariant functor from the category of finite sets into the category of sets. And it's given just by the expression that N of X is equal to the set of all groupoid morphisms from this pair groupoid of X into G. Or you can sort of imagine that those Gij's, they are somehow holonomies of some flat connection or something like that. So they should satisfy these kind of things. Now, this is actually a symmetric simplicial set. Let me explain what's happening here, because this category of simplices that I put here, the category of finite sets, is not the standard one. So the way I'll be drawing it, so my finite sets will be always like drawn as just a sequence of points. So let's just take that for every n, we will have just one finite set, which looks like that. Morphisms will go upwards. And if you have a map, then, well, it's represented by who goes where using these curves. And for the standard simplex category, one would take only order preserving morphisms or maps as morphisms. So we couldn't have these kind of crossings, but I do want to have these crossings. So that's why this thing is called, will be called in the end a symmetric simplicial set. And if we want to be really fancy about this category of finite sets, I can say that it's a symmetric monoidal category, which is generated by a single object. So that single object is this single dot. Now you imagine that having 5 dots, it means like dot, tensor, etc. 5 times. And what those dots can do, they can join, and that corresponds to having a product. So it's like a map going from dot, tensor, dot to a dot, which is a commutative and associative product. Here, like nothing incoming means that we have a unit. So we can also say that this is a symmetric monoidal category generated by a commutative algebra, or commutative monoid is probably the right word. And the really right way how to say it is that this is the prop of commutative algebras. So the universal one, universal symmetric monoidal category, blah, blah. But okay, that's only if you want to be fancy. Let's not be fancy, and let us return back to this nerve, which is just this easy thing. So if you try to see how big it is, what it is. So if you take n of n dots, so that is, we can identify naturally with g power n minus 1, because it's enough to specify those holonomies between consecutive dots like that. Anybody else is then fully determined by those equations. Like going from here to there would be the product of these two, and going backwards would be the inverse of that product. And also, basically, by this observation, we can now recognize the nerves of groups among all possible contravariant functors going like this. This is what is called the Siegel condition, or it's a like super easy case of the Siegel condition, which says that a contravariant functor is the nerve of a group if and only if, like this map, going from n of n dots to n of 2 dots power n minus 1. So when we see what's happening for each consecutive pair, so if that thing is a bijection for every n, so that's the thing which is written here, and plus 2 little requirements for small n's. So you see, I also have like empty set inside. So technically, this is really augmented simplicial, symmetric simplicial set, but that's not important. Okay, so this is how one can recognize nerves. And if you have a nerve, then it's easy to get back the corresponding group. What is the group? The group is just n of 2 dots. And how we can get the product on the group that's using this kind of picture. So let's say we take this n of 3 dots, that's what's drawn here, which using the Siegel condition is now identified with the group times group. And then when we use this morphism, so by functoriality, we'll get a map now going from here to there, and that's the product in our group. It's just what's drawn here. Yeah? So going straight from here to there corresponds to taking g times h. Okay, and now I'll try to do the same, but for commutative Hopf algebras. So you see, a commutative Hopf algebra, that should be thought of as just algebra of functions on a group. That's basically the end of the story. So let's say our commutative Hopf algebra will be the algebra of functions on G. Then we will define the nerve as the algebra of functions on this guy, or just the algebra of functions on this thing. So then this nerve will now be rather a covariant functor from finite sets to commutative algebras, just like that, right? The Siegel condition will stay as it is. Just what will happen, the only thing that happens is that the arrow gets reversed because it's a covariant functor now, and instead of the ordinary power, we'll get tensor power. So that's what it roughly looks like. So let me actually show you when it's written down. Yeah, so now this nerve of a commutative Hopf algebra is a functor going from finite sets to commutative algebras in whatever is our underlying symmetric monoidal category. The Hopf algebra itself will be then n of 2 dots. And since it is so simple, let me needlessly complicate things saying that such a functor going from finites to commutative algebras in C is the same as just a functor going from finites to C, but with an additional structure. That additional structure is that it's a symmetric Lax monoidal functor. We already met the statement that this finites it's naturally a symmetric monoidal category where, like, when you see a sequence of dots, it's just tensor product of those dots. And since I never remember this, the meaning of these words, let me show you what it is, even though it's not very important, as I told you. So what is a Lax monoidal functor? So if you have two monoidal categories, Lax monoidal means that we have these kind of natural transformations between the product and product of f's and f of products, and also something for the unit. But Lax means that we don't require these c's to be invertible, just that. Here is a drawing, how to draw such things. So my morphisms go upwards. So that's this morphism, which goes from fx times fy to fxy. This is this C1 thingy. And maybe one way how to remember what is Lax monoidal is that it's exactly what is needed so that f would send algebras to algebras, or monoids to monoids, if you wish. Because if you have like an algebra, so then we move it here and then we apply the product. So that's how f of an algebra becomes an algebra. And now I can kind of briefly, it's not really important, explain you how it comes that our n will get upgraded to a functor which goes to commutative algebras is just because this dot power n is naturally commutative algebra always. So here it is drawn for just two dots. So this is how n of two dots is an algebra, actually commutative algebra. But as I said, this was all kind of needless. So let me erase it. And let's get back to this easy thing that we have a functor going to commutative algebras or going to C, as you wish. And now there was this Siegel condition. So what is the Siegel condition? How do we recognize nerves of commutative algebras among all such functors? Here it's written, yeah, so we require that those maps going from the n minus first tensor power from n of two dots to n of n dots is an isomorphism and something for those small numbers. And these morphisms are now drawn here in a kind of nice way using that Lax monoidal structure. So that's maybe one reason why it's kind of nice to use that monoidal structure. Okay. Yep.
So, I think there is a question on the
chat.
Could you repeat again what does it mean, Lax?
Lax meant that those morphisms are not invertible or don't have to be invertible. It's this thing. That these things, they don't have to be invertible. So you see what's happening here. This is like a composition of two things. That first we apply those coherence morphisms, so the things that make the functor to a monoidal functor, and then we apply those joints. And all this is only that composition which is supposed to be invertible. Okay, maybe
I think there is one more question on the chat, but there I don't know, Ted, maybe you want to ask it yourself, because for me it's too complicated.
Hi. Yes, just to clarify. So, Pavol, so you spoke about group nerve just for groups, but you are speaking now about commutative Hopf algebras, but yes, aren't they just group objects in the category, well, dual to commutative algebras?
Probably you can deal with it like that. I'm fine with it. The reason, okay, let me tell you.
But I'm just, it's explanation just behind what you probably explanation.
Yes, you see, the reason why I'm talking about it now, because I want to switch to non-commutative Hopf algebras on the next slide, and that's why I want to like.
They, of course, non-commutative Hopf algebra won't be group objects.
Yeah. So I want to give you some picture for commutative Hopf algebras, and then we'll see that how it transfers to non-commutative ones.
Yeah, okay.
Okay. So yeah. So exactly as for groups, or maybe because it works for groups, as you now explained to us, we can say that commutative Hopf algebras, in whatever is our base category, are just equivalent to those symmetric Lax monoidal functors which satisfy this Siegel condition, exactly as for groups. The same thing. And here's how to reconstruct the Hopf algebra out of its nerve. That is just n of 2 dots. This is what used to be the product on the previous slide, if you remember. So now it's the coproduct, precisely the same thing. That's the product which I showed you just before, how things actually turn to commutative algebras. And this is the antipode, which makes sense that if you have like this holonomy between 2 points, then to get the inverse, you can just switch those 2 points. Yeah. Okay. So yeah, maybe I should summarize what happened here. So as you explained, does nothing. Yeah, so this is precisely whatever happened on this slide was already explained in the case of groups. So really nothing happened here. But now I'd like to do the same thing for non-commutative Hopf algebras. And the question is, can we somehow keep this stuff by changing it just a little? It turns out that yes, we can. The only thing that we need to change is this simplex category. So the category simplices. Instead of finite sets, we will have some kind of braided version. So let me show you. Here it is. This is this BR set. Now it has the same object, but morphisms are these kind of braids which go somehow non-bijectively upward. So when they arrive there, they can join each other. And they don't have to arrive at every point. We have this kind of relation, so we don't care about how they are braided when they somehow meet together. So another way how to say this, we have a braided monadial category, which is generated by this single dot. And that single dot is a commutative algebra. So it's commutative, that's this thing, that's this commutativity. And more precise, it is the braided prop of commutative monoids or something. Okay, but it's whatever are those words, it's a nice simple category. It's just this one. It's quite geometrical. And then this previous theorem just stays exactly as it was. That Hopf algebras, but okay, with invertible antipodes in whatever is our base in braided modular category C are equivalent, or their category is equivalent to the category of braided Lax monoidal functors satisfying the Siegel condition. The Siegel condition is the same as before, so nothing changed here. So what it was this one. And so it works also for our braided sets. And okay, and here are at least some of the operations. I didn't write for you the unit and the co-unit, so that's an exercise if you wish. Now, how difficult it is to prove this theorem? So one thing that we should prove, we should just verify that H with these operations is actually Hopf algebra, and that's easy. That's because since it worked for commutative in the case of commutative Hopf algebras, there is no reason why it shouldn't work here. It only if things got somehow entangled, but it just doesn't happen. So what is slightly more fun is to understand how to construct the nerve of a non-commutative Hopf algebra. So this is how to get Hopf algebra out of its nerve, but how to get n out of H. So let me show you at least briefly how to do it. Yeah, so we want to obtain a functor out of a Hopf algebra. Now we use just the Siegel condition to identify n dots with H tensor power n minus 1. Okay, so the only interesting thing is now to understand what's happening for morphisms. So I'll just show you an example. So how does it work for this example? It should be a morphism going from H power 3 to H power 2. You should somehow imagine that those three H's, they live on those links between consecutive dots. And here's how it works. So I'll write some kind, this formally an element A tensor B tensor C sitting in this H power 3. Now, the next thing, we interpret this morphism as some kind of picture. So let us separate a little bit like those two meeting strands so that they don't arrive at the same point. So that they now arrived at these two slightly separated points. So it's now a true braid, this morphism. And Now, I will interpret it, or let us interpret it braid as a kind of isotopy of the plane. And let us take this line and let's see how it moves with that isotopy. So in some of those 4 points, they will do something like that. And then the line itself, it will in the end up looking something of this sort. So whatever was this A segment, it will go now like here. Now this will be B stretched like that. C is here, and then it goes back to infinity. Okay, and now out of this A, B, C, I should produce some kind of X and Y sitting on these two links, like these two segments. And how do we do it? Well, we just draw transversals and now look at things that we meet on the way and multiply them from bottom to top. So you see here we're meeting A, but our curve underwent a positive half turn. So we apply the antipode of A, antipode to A. Then we meet B. Now the net number of half turns is 0. We're back to the original orientation. But we cross it twice, so we need to somehow apply the coproduct. So as many times as needed. Here is only once. So B is split by the coproduct into B1 and B2. Okay, and so here we just have this SA times B1, and here we have see here we have the inverse of the antipode, because now we have a -1 is the total number of half turns that we foresee. Okay, so that's roughly it. That's our functor. And finally, okay, it's supposed to be a braided lax monoidal functor. So I should tell you what is this, what are those coherence morphisms. So it should be a morphism going like this from a power of h times this power of h to this power of h. You see there is one more h here than here. So there is one h missing. So what do? We simply insert 1 into that thing, the unit of the Hopf algebra. So I don't know, this is some kind of combinatorial game. In the end, one can say that all that is drawn here is that basically the coproduct is done horizontally, product is done vertically, and one needs to count the number of antipodes and be careful about it. That's all. So it's maybe a nice game, but let's not forget that we want to quantize Poisson Hopf algebras. So the next thing that we should do, we should find the same kind of theorem, this theorem about nerves being equivalent to Hopf algebras, either commutative or non-commutative, but now for Poisson Hopf algebras. So what shall we do? We shall find yet another simplex category, and then the theorem will be the same. So in place of either finite sets or those braided sets, we'll have something which is in between, a kind of semi-classical deformation of finite sets to braided sets or something like that, like the first order deformation. And now this like theory of braided monoidal categories, there is basically a reasonably standard notion of infinitesimally braided monoidal categories, which is that imagine that you have a symmetric monoidal category, that's our finite sets. But then we deform the symmetry to a braiding by adding one more natural transformation followed by the symmetry. But we multiply it by epsilon, where epsilon squares to 0. So it's only the first order, a first order deformation. And then, okay, we want this thing to be like this sum to be a braiding, which then gives some properties for these natural transformations, which are called coords. I mean, those. So the morphisms in our now this coordinate set, the category of coordinate sets will look like morphisms in finite sets, but plus there would be occasionally these kind of horizontal chords connecting some strands, and they need to satisfy some reasonably nice relations, which are called Drinfeld-Konner relation or infinitesimal braid relations. I will not write them down for you. I'm just telling you that such a thing exists. There is one more relation that we're having here, which was this commutativity, which now like semi-classically looks like this. Okay, so this might be slightly more complicated category, but it's still reasonably nice. And then once we have it, we have the same kind of nervish theorem as before, which says that now Poisson Hopf algebras in a linear symmetric model category, or even in an infinitesimally braided model category, if you wish, that they are equivalent to their nerves, which are, again, infinitesimally braided, Lux monoidal functors, now from those coded sets. So this is our new simplex category. Okay, and they need to satisfy the same Siegel condition as before. So nothing changed. It's kind of pretty thing that the only thing that you need to modify is the category of simplices. You need to put just enough of braiding inside. And the operations are kind of the same as before. So here is just this one new thing, which is the Poisson bracket, which somehow you can understand that it comes from, well, now we somehow have this first order deformation. So this will give us that Poisson bracket. So it's all good. And here we are. So now we can quantize things. So how do we quantize things, or what do we actually want to do? So imagine that we have a Poisson Hopf algebra in C, meaning that we have its nerve. So it's a functor going from chorded sets to C. And we want to obtain a Hopf algebra. In other words, a functor which goes from braided sets to C. Ignore this PA for the moment. It's nothing important. So how do we do it? We just do it in one step for all possible Hopf algebras. There would be, we'll just find one universal functor going Q, going from braided sets to chorded sets. And then we get this thing just simply as the composition of Q with that. So that's the end of the story for the quantization. Now, still I should tell you what the Q is. So first, let me tell you what that PA braided sets, they are parenthesized braided sets. It just kind of simplifies that Q. So it's a category which is equivalent to braided sets, so nothing changes. I can perfectly replace braided sets with those parenthesized braided sets. And basically, what happened is that it's no longer a strict monoidal category. So now we need to have a parenthesization of each of the objects. So as we multiply those things, those dots, we need to remember how exactly we multiply them. But the morphisms just don't care about the parenthesization. So that category is simply equivalent to braided sets. So nothing happened here. And then this quantization functor, it goes from this parenthesized braided sets to chorded sets. And the way how it's done, well, that's an already reasonably old idea of Drinfeld, how to basically turn anything infinitesimally braided to braided. So the way it's done is that we send like this braiding or this overcrossing to crossing, which is here, composed with the exponential of h bar over 2 times the chord. We do nothing for the product. So when those two strands meet, we just leave it as it is. And then finally, that's the real deal here. So what one should say, what happens if you change the parenthesization? So if you take the morphism where these two things are parenthesized, I'm going to the same kind of thing, but where these two dots are parenthesized. So then this has to be sent to a Drinfeld associator where you put for the variables the chord on the first two things and the chord on the second two things. So this requires a bit of some kind of higher technology. If you're willing to live with complex numbers instead of rational numbers, then we can take the associator which comes from the Knižník-Zamolodčíkov equation. So then the coefficients will be multiple zeta values. But as Drinfeld proved, there is an associator with rational coefficients if we want it. Okay, so that was this quantization of Poisson Hopf algebras. And I hope it was not too fast, because I want to tell you about where it came from. And the reason why I want to tell you about where it came from is that I think that there are still many other similar things hidden there, which were not fully explored. And so I hope that somebody at some point will look at it. So now I'll tell you about some kind of moduli spaces of flat connections on surfaces with decorated boundary, which is a work that we did with David Lebland a few years ago. And it started even earlier, sometimes like, I don't know, probably in the previous millennium, with what's called the Lu-Weinstein double symplectic groupoid. So what is that thing? So if you take a Poisson Lie group H and its dual H prime sitting in the same Drinfeld double G, then they constructed a double symplectic groupoid gamma, which sits both over H and H prime, which is some kind of symplectic model for the quantum group in some sense. So this thing beautifully contains in the idea of duality in between those two Poisson Lie groups. And what it is, probably the easiest way how to describe it is as a moduli space of flat connections. That's the reason why I'm talking about it here. That we take flat G connections on a square, but with some boundary conditions. So now I want this connection on those blue sides to have values in H, and on those red sides to have values in H prime. So again, gamma is what it's like this holonomy, which is in H, and another which is in H prime, and another in H prime, and another in H, plus a condition, and this times that is equal to that times this. So that's exactly the description of Lu-Weinstein of this double groupoid. So why is it useful to see this moduli space? Because it also has a symplectic form, and the symplectic form is the Atiyah-Bott symplectic form. And okay, now how is the double groupoid? So you can imagine if you have two squares, so you can either compose them like this or like that. And it is a groupoid because if you want to compose them, if you want to glue them, then those two vertical holonomies which you're gluing, they have to be the same. But this way, it's not entirely obvious that it's a symplectic groupoid. So then it's better to write the composition as follows, one of those compositions as follows, that we'll take this kind of three-dimensional cobordism, which is colored, with boundary colored by those two colors. And now consider those flat connections on these three squares. So there are three squares, which actually extend to a flat connection on this cobordism. And by the whatever general nonsense, you will get a Lagrangian submanifold in the product of these three. And yeah, that's the graph of one of those two products of gamma. So the other one is given by a similar picture, but with exchanged colors. And maybe even better, like say, why is it interesting conceptually? Because what should really be happening that we should be considering Chern-Simons theory with the group G. And this would be some kind of diagram for the Chern-Simons theory, or whatever, some particular cobordism for the Chern-Simons theory. And the vector space which is assigned to this square, that should be the quantum group itself. And this would be the product in the quantum group, and with the exchange things, it would be the coproduct of the quantum group. Of course, it's another question whether that Chern-Simons theory with these boundary conditions actually exists and things like that. But say this is where the interpretation of such a thing. So why such a thing should exist? And with David, we then looked at moduli spaces with decorated boundaries, some more generally, and we noticed then that many Poisson or symplectic manifolds which appear in the theory around the theory of Poisson Lie groups actually are very naturally moduli spaces with some boundary conditions. So let me just tell you to be precise what I mean by that. So we take the moduli space of flat G bundles, and now whenever you see some kind of arc on the boundary and we choose some particular color, so to that color we assign some particular subgroup in G, like this is H sitting in G. And we now consider, okay, so we want to have a reduction of the structure group over that colored segment. So to have a flat H bundle would be here, and this would be a flat H prime bundle. And what is happening at the vertices? So the simplest thing that one can do is to require that those two reductions are compatible. Right, there are two principal subbundles sitting in the same principal bundle. Compatible means that they intersect. And then it's somehow convenient to actually choose a common reduction to only to the connected component of the intersection. There is another option that we don't require them to actually intersect, so we don't have to be compatible, and then we should just choose an element from this double coset thingy, just to say what is the mutual position of those two bundles at that point. But I'll be using only this upper thing, and everything is then extremely simple. So here's our Lu-Weinstein double groupoid as before. This thing is going to be just the Poisson Lie group. So the only thing that we're having here is the holonomy from this vertex to that vertex. That's the only invariant thing that which remains. So this modular space is simply equal to H, and the Poisson structure is the Poisson structure on H. And it's sort of reasonable that it looks like half of this double groupoid. That's what it should be. But put better, so how do we obtain the double groupoid from here? It's obtained by doubling the surface. So let's take this surface, this rectangle, and then take it with two layers. And we need to then glue those two layers along this uncolored edge. So that uncolored edge is where we don't reduce anything, or rather, I can say that we reduce to the original group G, which is still quasi-tropic, so things still work. Here's whatever, for people who like it, here's a picture for Poisson homogeneous spaces in general, which are somehow classified by a Lagrangian subgroup in G. There's the picture of the Drinfeld double. And so what is this guy? I didn't write it. There's the symplectic groupoid integrating the Drinfeld double. And why is it so? Because it's, again, this surface can be obtained by doubling of this surface, precisely in the same way. And yeah, now if the talk is too boring or something, you can now amuse yourself and try to find, this should be a double symplectic groupoid. So try to find those two products using cobordisms. One of them should come simply from the doubling. So each time you double something, it is automatically the symplectic groupoid of the thing that which you doubled, and you should automatically somehow, we should find general procedure how to get a cobordism, but there would be one more product. Okay, very good. So let me summarize this as a kind of principle that any relevant Poisson manifold is a modular space, and every relevant quasi-tropic submanifold or a Poisson map will come from a cobordism, or in some very easy cases from a surface embedding, which the surface embedding should be seen as poor man's version of cobordisms. Or put more bluntly, just everything is Chern-Simons theory. So that's what this slide is supposed to mean. Yeah, maybe I should add a few things. So if all those boundary arcs, if they correspond to Lagrangian subgroups, then we're getting a symplectic manifold. So our modular space is symplectic. If there is something which is just quasi-tropic like that, then our modular space is going to be just Poisson. But the Poisson structure is just the same way as the symplectic structure is of this Atiyah-Bott type, meaning that it's simply given by the intersection pairing on the surface itself. Okay, so this was some kind of general story. Now with David, we'll not just introduce those or study those modular spaces, but we also found that deformation quantization, but not of all of them, but only of those where those colored arcs are separated by these uncolored arcs, where there is no reduction happening. Fortunately, say for quantization of a Poisson Lie group, it's not a big problem because we have a local I mean, those two things are locally diffeomorphic, so we can simply then pull back the star product from here to a star product there. But say for a Poisson homogeneous space, as we saw it before, for these kind of things, it wouldn't work. So we cannot quantize those. If you want to know how exactly they are locally diffeomorphic, just cut off corners from this rectangle, just those two upper corners, and you will get this picture. And so each time you have a flat connection on this guy, it will restrict the flat connection on this thing, the thing which is obtained by cutting those two corners. So this gives you a map from the moduli space to the moduli space. And yeah, so if you want to have like true equality, what is needed is that every element of G should be decomposed in a unique way as a product of an element of H and H prime. If it doesn't happen, then we only have this local diffeomorphism. Okay, so how do we do it? We actually didn't start with those colored things. We looked at slightly different moduli spaces where we still have some kind of these kind of thick arcs, but there we reduce the structure group completely. So it will trivialize the bundle. There's a flat trivialization at each of those black arcs. So these kind of moduli spaces still carry a bivector field, which can still be obtained by suitable intersection pairing on the surface, but it's no longer a Poisson. So that's work of Alexeyev, Constant, Schwarzbach, and Meinrenken. So they first of all introduced this notion of quasi-Poisson manifolds, and also explained how these kind of moduli spaces are actually quasi-Poisson. Now, since these are not Poisson manifolds, then we cannot possibly quantize them to associative algebras in the ordinary sense. But there is a way how to do it anyway. So it will be the associativity will become non-trivial. So we'll quantize it into algebras in some suitable braided monoidal category. And then if we want to now come back to our nice Poisson moduli spaces, what should we do? So what is this space anyway? So you see, we have one holonomy which goes like this, which is an element of G, another holonomy which goes like this, which is another element of G. So this moduli space will be just G times G. And to get that thing, what should we do? We should simply mod out by the action of H here and by the action of H prime here and there. So mod out by gauge transformations. That's all there is. Now for functions, what it means that we take functions which are invariant with respect to those respective colored groups. And once we do it, well, this product, or this deformed product here, which was somehow not quite associative or strangely associative, it will become an ordinarily associative product, and that's it. That's our quantization. So now, let me tell you where exactly are we quantizing, and so what does it mean, this non-trivial associativity? Sorry for going back to categories after this little bit of geometry. But it's basically the most standard braided monoidal category which one can meet in this context, which was again introduced by Drinfeld. So the category is simply the category of representations of G, but with a new braiding and also a new associativity constraint. So what really happens is that this category of G representations, once we pick say an inner product of G, which we had always when this was a Drinfeld double. So once we pick some T which sits in S2G, which is G invariant, then we can make this category to an infinitesimally braided category. So the single chord will be just obtained by applying T on this representation and the other end of T on that representation. And that will give us a new braiding. So it's no longer symmetry, and a new associativity constraint. So new way how to pass parentheses from here to there. Okay, so this will be our category. But what we are interested in, we want to construct algebras in this category. So how can we start? We only have 2 tricks, so there is not much to know here. The first thing is to try to construct commutative algebras, commutative and associative algebras. And let's take things which are of geometric origin. So let's take just a manifold on which we have an action of our Lie algebra. So then C infinity of M is a representation of G. It does have its standard product. And it turns out that if the action is kind of very nice, if it has quasi-tropic stabilizers with respect to this inner product, with respect to the T, then C infinity of M simply stays commutative and associative even in this crazy category. So why is it so? Because this condition of quasi-tropic stabilizers is precisely this condition, that if you take 2 functions on M, then apply this chord thingy and then take their product, and this is 0. That's a translation of what quasi-tropic stabilizers mean. And that then means that all this strange stuff appearing in this exponential or in the associator will just die. It will all go away. If you want to verify whether it's commutative or associative, from this exponential you will keep only 1, and from this associator you will also keep only 1. So anything which contains at least 1 chord is just disappears. Okay, that's nice, but we want to get non-commutative algebras. These are too easy. So this is our second trick, which is like this really stupid one, that if you take 2 algebras, if you already have 2 algebras, maybe they are commutative, maybe they are the ones which we constructed this way. And if you take their tensor product, so if you take A tensor B, then it is again naturally an algebra, like just in this way. So we simply exchange A and B like that and then multiply. And now this algebra is usually going to be non-commutative. So non-commutativity is born from this braiding here. So that's the end of our tricks. To be like super precise, I should tell you that instead of having 2 G algebras, we might actually have 1 G plus G algebra, and then we turn it to a G algebra by taking only the diagonal action of the G, and the product which you obtained, and this deformed product would look like the old product composed with J, which is this thing. But what is the J? The J is simply this lower part of the diagram. And in general, just don't worry about what I told you right now. One should simply think of whenever you see J, it means tensor product. Okay, and only to recall, so after all this stuff, so if you end up with some nice algebra in this strange category, and if you take a coisotropic Lie subalgebra of G, then when we take the C invariance inside, so that's going to be a subalgebra. It's closed with respect to the product, but it is also a nice ordinary associative algebra. So one way how to say it is that taking C invariant is a braided Lax monoidal functor, if you wish, from this category to vector spaces. But let me not say it like that. It just, all that happens that in the end we can kill that associator simply by taking invariance with respect to big enough Lie subalgebra. And that way we obtain an ordinary associative algebra. Okay. Now, so how do we actually quantize those quasi-Poisson moduli spaces? So here is a surface. There are those thick black arcs where the bundles are supposed to be trivialized, and I put there also some signs, pluses and minuses somewhere in a random way. It's sort of a technical thing, but it's also, in a way, it's conceptual. So one should think of those minuses as incoming arcs in some sense, and those pluses as outgoing arcs. And so we take the moduli space of the thing. So those pluses and minuses don't play any role in the moduli space. Don't worry about that. And what we want to get after the quantization, we want to get an algebra in the Drinfeld category where we have we have G power n plus G bar power n minus acting. So G is just G, and G bar is G with minus T. So we somehow we just change the sign of the inner product. So that's okay. So that's what we want to obtain. This should be it should be just the algebra of functions on the moduli space, and we should be somehow that's what we should get. And how do we get it? Well, we start with, as I told you, we start with a commutative algebra. So we start with some easy building blocks, this kind of magnets. So we take a rectangle with 1 minus and 1 plus. The moduli space is just G, just the group G. There is just this one holonomy. And to that, we simply take C infinity of G with its original product. So we don't have to deform anything in this case. Why is it so? Because that's exactly the case when we have action of G times G bar on this moduli space, and these stabilizers, which are basically is the diagonal G, are coisotropic, in this case even Lagrangian. So we can do it. If you take several of them, because we want to take several of those building blocks, then we just get C infinity of G power K, but things are exactly as before. Okay, and now out of these building blocks, we will try to glue our surface. And there are just some easy rules. So whenever we can somehow try to join two thick things marked with 2 pluses. So we can do it as it's drawn here, but those pluses don't disappear completely, so they appear on the top now. Or we can do the same thing with minuses, and they will appear on the bottom. And the operation that we should do with the algebra is simply that we apply the tensor product. So there is this composition with J here appearing. So these operations, these two, they don't change the moduli space. The moduli space is isomorphic, or the algebras they are the same vector spaces, but now here we have action of G and another action of G. Here we have only one action of G in place of that. Then there are some kind of destructive operations where you can join a plus with a minus, or another operation where you simply remove a thick arc. So we would simply take this thing and draw it the same thing, but without that thing, thick thing. So in that case, we simply take invariance. So here we would take invariance with respect to the diagonal action. Here we would simply take the invariance of the action of G. And we don't need to change the product in any way. So this is like taking invariance with respect to a coisotropic subalgebra, as it appeared on the previous slide. Okay, so these are the operations, those are the rules that one should do. It's only here when the product is modified. Here, nothing is modified. And in the end, once you build that surface, you will get the quantized moduli space as an algebra in this stuff. Okay, now one thing that when we were doing with David that we didn't know, we hoped it was true, but we couldn't prove it. But now Jan looked at it and proved it, so which is really, really great, is that the algebra that we obtain is actually, in some sense, independent of the cutting, independent of the way how we build it. More precisely, there are whichever way we get it, those things are always canonically isomorphic. So there are some coherent isomorphisms. And also this thing is then functorial under embeddings of surfaces, as long as that embeddings respects those thick arcs. And ideologically, what one should understand, how one should imagine it, is that these thin parts of the boundary, they are kind of fake. So what one should do, one should double the surface and glue it along those thin parts of the boundary. And so in the end, we obtained a surface with simply boundary circles. So each time, for example, from this, we would obtain a cylinder, right? So this would be one circle, this would be another circle. Okay, and now let me let me connect those two parts of my talk. So let's just try to quantize a Poisson Lie group now with this new method. So our Poisson Lie group is just this moduli space. So how would we quantize it? First, we need to build this thing. So then we simply take two of those magnets and join them, or fuse them, that's the right word. We obtain this moduli space. And then we need to take invariant, so mod out by h and twice by h prime. There are actually two ways how to do it. We can either do it as here or as there. And it turns out that this thing corresponds to a thing of Kazhdan quantization, and this thing corresponds to the quantization which I described at the beginning of my talk. So somehow to relate those two quantizations, you need to turn things by 120 degrees. Okay, but what happened here? You see, with this quantization, we only quantized H as a Poisson manifold. We didn't quantize it to a Hopf algebra. It's only now, yeah, we only have a star product on H. So how can we obtain, okay, how can we also obtain the coproduct? So we should be looking at the product on H, right? So that's what corresponds to a coproduct. And one reasonable idea is to look at other moduli spaces. So let's look at this one where we have now three red arcs. So when we think of it, this guy is now actually like Poisson isomorphic to H times H. So this is a way how to get it. So let's plug in one H as subsurface, another copy of H as a subsurface. So then we will have a map from this moduli space, from this big one, to the product of those two H's. And it is, well, locally a diffeomorphism, and it's, of course, it preserves the Poisson structure. And so in this sense, this moduli space is simply H times H. And now we should see how to get the product, the map which goes from H times H to H. Okay, so for that, we simply can place our small moduli space again as a subsurface here. And that way we get really that map going from H times H to H. So then we can basically do the same stuff with those quantized algebras. And so this is how our nerve actually appears. So our Hopf algebra is supposed to be this quantized algebra of functions on H. A nerve of any number of dots will be this quantization of this kind of moduli space with several dots. So that's roughly what's happening here. But to really make this story coherent, one should ask what kind of cobordisms or things like that in Chern-Simon's theory will actually persuade, like give us our Hopf algebra. You know, what do I want to say? That first of all, this surface should provide an algebra, but Chern-Simon's theory, as I naively understand it, it will assign to a surface just a vector space. If you want to get an algebra, you need to have also some cobordism. Okay, so what one should actually do? We need to double the surface. So again, when we double it and glue it along those black parts of the boundary, those thin parts. So what we obtain is then simply a sphere with 3 holes, and 2 are red and 1 is blue. Similar thing here, right? So we have 3 red holes and one blue hole. In other words, what is the thing which corresponds to doubling of this? That's the top of this surface, right? So sorry, the top of this cobordism. And now I try to redraw for you what's happening here with those embedding of surfaces. Now using the doubled surfaces and turning embeddings to cobordisms. So these 2 triangles, they are now on the bottom. They correspond to doubling of this guy, right? So there is a there is a blue boundary and 2 red disks. And Yeah, and then those red parts of the boundary, they are inside, there are these tubes which somehow join, and the blue part of the boundary is there's this blue outside. So what do we see here? It's actually our likes braided monadial functor and also that category BR set. So this blue outside, when things can, so it somehow contains things, and there might be several blue tubes which can join. That corresponds to a functor together with a braided Lux monoidal structure. And those joining red tubes, they correspond to that category of braided sets. So this in the end is the picture. Now, of course, the picture is only ideological, but the reason why I'm talking about is that one can imagine many other types of pictures, and it's quite probable that they would give us some interesting new stuff. So let me just briefly mention some open problems and what one could do with it. This would be the end of the talk. So if we try to, so everything here was about Hopf algebras, so if you try to do something with Hopf algebroids, so if you try to talk about other things that have nerves, like groupoids, then we can try to do it, and it works very well, but it turns out that the base, the algebra functions on the base, which is n now of a single point, is always commutative. So one interesting thing is one interesting question is whether one can modify this stuff to get true Hopf algebroids. So maybe there is a hope coming from when we replace this Chern-Simons theory with the Courant sigma model. There is the second thing is of the same type. So if you look at the nerves of higher groupoids, so if you now relax the Siegel condition almost completely, so if you modify it to something different, so then these constructions, they still produce all kinds of Poisson or then also non-commutative algebras, but we don't quite understand what's happening here. So it would be really pretty to know what's going on. And finally, this is the true message. So the question is, what else one can extract from this ideology of Chern-Simons theory? Okay, so thanks a lot. That's all.
Well, Pavol. And so do we have questions? Anybody, questions?
Pavol, I might have a question.
Yeah.
So you were looking at a square where you have boundary conditions.
Oh, sorry, I cannot hear you.
Yeah, sorry. So you were looking at a square where you had boundary conditions coming from a Manin triple. Mm-hmm. So that's like a splitting of your Lie algebra into Lagrangian subalgebras, right?
Mm-hmm.
Did you imagine what happens when you just have a Lagrangian splitting without the requirement that they are subalgebras?
Oh, okay, this I don't know. Then I don't know how to use such a thing as a boundary condition.
I mean, the important thing for a boundary condition for me would be that it's Lagrangian, not necessarily a subalgebra.
Okay, but at least then it depends on what setup one uses. But we wouldn't get the solution of classical master equation, or it wouldn't be gauging variant put more simply. I just wouldn't know what it should mean to. No, I'm not saying that. I guess there is a meaning in the thing, but I don't know how to interpret it.
Yeah, no, I was just curious.
Mm-hmm.
Thank you.
Question from Pavol.
Yeah, I just want to ask maybe to repeat how exactly the two stories are related, the one in the second half and the one in the first half. So in the first half, you had this description of Poisson Hopf algebras and Hopf algebras via these functors, and then you had and both of them were Hopf algebras in vector spaces. Do I understand correctly that in the second half you lift them to the symmetric monodal or braided monodal category of representations of the Drumfeld double, and then you have forgetful functor back to vector spaces, which is lax braided monodal?
Yes, one can say something like that. Just in the first part, that there was, let's say, there were no Lie algebras, or there just things were more abstract. I don't know.
And one more question: can you encode bialgebras instead of Hopf algebras in some formalism like that?
Not that I know. So it was like that antipode was really important, and even the invertibility of the antipode was very important.
Okay, thanks.
Okay. Alejandro has a question.
Yes, hi, Pablo.
Hi.
At some point you mentioned this idea that you have a quadratic Lie algebra acting by quasi-tropic stabilizers on a manifold M, right? Yeah.
Sorry, I forgot the last thing.
Yes. Thank you, actually, for that. So from this, you could build a current algebroid, which is M times the Lie algebra, and the fact that has, yeah. So you could use this as a, let's say, to replace in Chern-Simons to a current sigma model. Is there any example of such an M that you could quantize using this?
I don't know, I have to say.
Okay. So
yeah, I know that. Since I worked with David, I definitely know about this construction of current algebroid like that. And I was thinking about it, but I didn't get to anywhere, so I don't know.
So this thing that you're mentioning that maybe generalize from Chern-Simons to a current sigma model.
Oh, that's just wishful thinking.
Okay, but it seems important that the body of this supermanifold, whatever it is, it's a point in the constructions that you have been doing so far.
Yes.
Okay.
But though in principle, okay, if I go very fast, wherever it was, like this type of thing, it can be used like to talk about those double symplectic groupoids, integrating Lie bialgebroids or things like that.
Right.
So as long as we stay with those squares, it's with this kind of diagram, it's okay. Just then, probably when turning into this stuff there, I'm not sure. One will have to think about what's precisely happening there.
Okay, thank you.
Actually, since you're on this picture, could you explain again what you mean by locally diffeomorphic? Do you really mean this?
There's a map. There is a map going from the moduli space to that moduli space, which is given by, as I said, that if you cut those corners, then you get just this surface. And that map is a local diffeomorphism. And it would be a global diffeomorphism. It would be like truly the same thing if like every element of G can be written uniquely as a product of elements of H and H prime. Because you see, here you have some kind, just imagine you have some kind of holonomy in G, and then you have to like reassign it to a part of it to go to this red part, and the part going to the blue part. And if you want to be sure that it can be done and in a unique way, then there should be this unique decomposition. But so there are examples of whatever Manin triples where it's not true, but in most standard examples, I think it is just true. So in usual examples, it would be just equality here.
Brent has a question.
Hi, Pavol. Thanks for your talk. I guess there's kind of two questions, but I think they're closely related, so maybe I can ask them at the same time. So the first thing I wanted to understand was, this procedure that you have for quantizing, it depends on an associator. So I guess at the end of the day, what you get is always perturbative. So it's a formal power series in H bar.
Oh, yes, yes, yes.
Okay. And I was wondering, there's another construction of quantizations for character varieties of surfaces using factorization homology, Bensby and Brochet and Jordan. I was wondering, I mean, the ingredients seem somewhat similar, but I can't see really exactly what the precise link between them is. Do you have any idea what it might be?
Oh, I would characterize my understanding exactly as you said it. Yeah, those things are definitely related, but I'm not quite sure how to put it.
Okay, thank you.
So I mean, their business is for like when they actually have a true quantum group, and then there's this category of representations, which is very nice. And yeah, this slightly different. It should be, yeah, it should still be the same thing, but I don't know how to say it precisely.
Okay, thanks.
Okay, I don't see any more raised hands. So if anyone else has a question, you can also just speak up if you don't know how to raise your hand. Otherwise, I would say if that's not the case, then let's thank Pavol again.
Okay, thank you.
And I believe next week, Alberto Cattaneo is going to be the speaker, if I remember correctly.
That's correct.
Great.
Okay.
Thank you.
Bye-bye.
Bye-bye.
Bye.